Good morning, everybody. Hope you're all healthy and safe at home. Let us begin a new section of our third module, section 17.6, exponential and logarithmic functions. So we are all familiar with the function, exponential functions and logarithmic functions, e raised to x, log x and all. So let's that is in case of real variables, right? So let's see what will be the changes, or what are the will there be any change to the corresponding functions in case of complex numbers. So in this lecture we'll be discussing about the exponential functions. So usually we define the exponential function by e raised to x. We are all familiar with that notation. So what will be e raised to z? E raised to z will be equal to, instead of z we are just substituting the value x plus iy, and this e raised to x plus iy has the expansion or has the expression of the form e raised to x into cos y plus I sin y. So from where did that expression come from? It is coming from the concept of the Maclaurin series, which you guys must have learned earlier, or if you haven't, just refer to it. It is given in the section 3.3 of your textbook. So e raised to, and this is an important formula like Euler's formula, which is called as e raised to iy is equal to cos y plus I sin y, where y is a real number. Okay, and they have given the explanation how has this come into existence. This is by applying the Maclaurin series for the expansion of e raised to x. Instead of x we replace it by iy. So actually e raised to x is summation k equal to 0 to infinity x raised to k by k factorial. Okay, so instead of x we replace it by iy, and when we apply the expansion we'll get 1 plus iy square by 2 factorial plus iy cube by 3 factorial plus etc. Okay, so when we taking the powers, clearly I square is minus 1, so the even powers will all be minus 1 plus 1 something, and minus 1 plus 1 minus 1 plus 1 and so on, and for odd powers we'll have I remaining. So in that manner we can combine the real terms and the terms without I separately. Okay, terms with I and the terms without I separately by just opening up the brackets. So this is the expression of cos y, and this is the expression of sin y. This is also same by Maclaurin series. So you guys can refer what is Maclaurin series if you guys are not remembering it or not familiar with it. So from this we can easily obtain our so-called definition, that is e raised to z is nothing but e raised to x plus iy. And what is e raised to x plus iy? That is e raised to x into e raised to iy. So we get this is equal to e raised to x into, and what is e raised to iy? Cos y plus I sin y. Just now we have obtained the expansion. So this is how we have obtained this definition of the exponential function, that is e raised to z is equal to e raised to x into cos y plus I sin y. So by using this expression we can prove the following properties of the exponential function. It is very simple to prove that. So let's just try to see it one by one. So the first one that we have to prove is that the function is entire. Now what is an entire function? Just recall that the entire function is said to be entire if it is analytic at all points in the given domain. Okay, and how do we check whether that function is analytic? For the analyticity we can verify whether the Cauchy-Riemann equations is satisfied or not. Okay, that is what we had done in the previous lecture. So let's just see how we can prove it. So we have to show that the function e raised to z is analytic, right? So the first property is e raised to z is entire. Now by our expression e raised to z is nothing but e raised to x into cos y plus I sine y. Okay, so just expanding this, I get this is e raised to x into cos y plus I into e raised to x into sine y, right? So now this will be our u and this will be our v. Okay, so what is the Cauchy-Riemann equations? Dou u by dou x is equal to dou v by dou y, and dou u by dou y should be equal to minus dou v by dou x. So let's just see whether these are satisfied. Now u is e raised to x into cos y, so what will be dou u by dou x? Differential of e raised to x is e raised to x itself, so dou u by dou x is e raised to x cos y itself. Now what is dou v by dou y? V is e raised to x sin y, so differentiating partially with respect to y, we get sin y will become cos y, so that is again e raised to x cos y, right? Again, now let's see the second one. Dou u by dou y. What is dou u by dou y? Dou u by dou y will be equal to differential of cos y is minus sin y, right? So e raised to x into minus of sin y. And what is dou v by dou x? It is just e raised to x into sin y. So we get dou u by dou y is equal to minus dou v by dou x. So the Cauchy-Riemann equations are clearly satisfied, and as this, and also we have seen that for the converse of this condition, that is, we should not only check whether the Cauchy-Riemann equations are satisfied, but I also have to verify whether the functions are continuous and all, right? So clearly it is just e raised to x and cos y sin y, trigonometric functions and exponential functions all are continuous, so there is no doubt in the continuity of all these partial derivatives as well as u and v. So u is continuous, v is continuous, the partial derivatives, all of them are continuous, and also the Cauchy-Riemann equations are satisfied, and so we can say that the function will be analytic at any point. So there will be no change in the analyticity of the given function. Thus, the given function is entire. Now let's see the second property. That is, in case of real numbers, what is if we are given the function e raised to x? What is the derivative of e raised to x? If f of x is equal to e raised to x, then what is f dash of x? F dash of x is also e raised to x. There is no change in it. So let's see whether it is true in case of e raised to z. That is, we are going to verify that if f of z is equal to e raised to z, then f dash of z is also equal to e raised to z or not. Okay, so if you just remember, in the previous section we had seen that, or to prove that if the function is differentiable, then it satisfies the Cauchy-Riemann equations. We know that, right? So we had seen the proof of that f dash of z can be written as dou u by dou x plus I into dou v by dou x. Okay, or it has an expression in y also, that is f dash of z is equal to minus dou v by dou y plus I into dou u by dou y. Okay, this is the expression. So we can use any of these expressions to check whether f dash of z is e raised to z itself. That is, f of z is e raised to z. E raised to z has the expression e raised to x into cos y plus I sin y. So by using this expression, we can see that f dash of z is, here what will be u? U is e raised to x cos y, and v is equal to e raised to x sin y. So dou u by dou x is e raised to x cos y itself, and plus I into, using this expression, okay, I'm using this equation. And what is dou v by dou x? Again e raised to x into sin y. So this is nothing but same as e raised to z. So f dash of z is also equal to e raised to s. If we use this equation also, we will get the same expression. Why? What will be dou v by dou y? It will be nothing but e raised to x into cos y, and dou u by dou y will be minus e raised to x into sin y. So it doesn't change, the values will remain the same. So you can just verify that if you have any doubts. So now we have shown that, so this is no longer a question mark anymore. That is, if f of z is e raised to z, then f dash of z is also e raised to z. Now what is the another property? That is f of, this is the third one, right? F of z1 plus z2 is equal to f of z1 into f of z2, where f of z is the function e raised to z. Okay, that is like if you are given e raised to x plus y, we know that it is nothing but e raised to x into e raised to y in case of real. So we are just going to prove the same thing here. So, or this I can write in terms of exponential function, that is e raised to z1 plus z2 is equal to e raised to z1 into e raised to z2. So let's see whether it is true or not. So what will be f of z1 into f of z2? It will be e raised to z1 into e raised to z2, and which is again e raised to x1 into cos y1 plus I sin y1 into e raised to x2 into cos y2 plus I sin y2, right, where z1 is equal to x1 plus y1 and z2 is equal to x2 plus iy2. So I'm going to take this e raised to x1 into e raised to x2 common, and I'm just going to multiply this. What will be cos y1 into cos y2, right? Then plus I into cos y1 into sin y2 plus I into sin y1 into cos y2. I'm just opening up the brackets. Then I into I is minus, so I square is minus 1, right? So we get this as sin y1 into sin y2. So if we combine the imaginary terms and the real terms together, we get cos y1 cos y2 minus sin y1 sin y2. So what is that expression? That is nothing but cos y1 plus y2, right? And the other expression, that is of the imaginary part, cos y1 sin y2 plus sin y1 cos y2, is the expansion of sin y1 plus y2. And this is both real numbers, so this is nothing but e raised to x1 plus x2 into cos y1 plus y2 plus I sin y1 plus y2. Okay, so this is equal to the expansion of f of z1 plus z2. So this can be easily proved, all these can be easily proved by using the definition that we have given, that is f of e raised to z is equal to f of z is equal to, or e raised to z is equal to e raised to x into cos y plus I sin y. Okay. There is another property of division also, that is e raised to z1 minus z2 is equal to e raised to z1 by z2. So you guys can just try it out on your own. So once we have defined the exponential function as e raised to x into cos y plus I sin y, we have the following properties, that is the exponential function is entire, and the derivative of exponential function is same, and f of that is e raised to z1 plus z2 is equal to e raised to z1 into z2, and e raised to z1 minus z2 is equal to e raised to z1 by e raised to z2. Now next is a concept of the periodicity. That is, if you guys just remember or recall in your mind the graph of sine and cos and all, after a particular interval the same graph is being repeated again and again. So the sine function and cos functions are periodic, and in the expansion of e raised to z we have these functions, and so we can say that the function e raised to z will also be periodic, and it has the complex period 2 pi I. This will be the period of the function e raised to z. Okay, that is f of z plus 2i will be equal to f of z itself. Now for just the verification of that, we can see that by just using this expansion we can easily see that this is true. Why is it true? So let's see. We have e raised to z is equal to e raised to x, right? E raised to z is equal to e raised to x into cos y plus I sin y. Okay, so what will be e raised to z plus 2 pi I? This will be, or we need to find what this is. Now we have seen in the expression that e raised to iy is nothing but cos y plus I sin y, right? So what will be e raised to 2 pi I? It will be cos 2 pi plus I sin 2 pi. Now what is sin 2 pi? This is 0, and cos 2 pi is 1. So we get e raised to 2 pi I is 1. So we have e raised to z plus 2 pi I will be equal to e raised to z into e raised to 2 pi I, right? And we have just now seen that e raised to 2 pi I is 1. So this is equal to e raised to z itself. So after a period of 2 pi I, what happens is the function is repeating again. Okay, so that is why we say that the period of the exponential function is 2 pi I. That is a complex period of the exponential function. Okay, so f of z plus 2 pi I will be equal to f of z itself. Now we'll move on to one more point regarding the exponential function, that is the polar form of the exponential function. Okay, we know any polar form, any complex number can be expressed as the corresponding polar form, right? That is, if z is a complex number, then the polar form is given by z is equal to r into cos theta plus I sin theta, right? So what will be cos theta plus I sin theta? By our expansion, it is nothing but e raised to I theta. Okay, so that is actually the expression of z. That is, z will be equal to r into e raised to I theta will be the polar form of the exponential, or polar form of any complex number. And in polar form also we can bring the exponential function into the picture. So we'll just see a few there is just two examples that depicts the concept of this complex value of the exponential function and the corresponding polar form and all. So let's see what is example 1 in your textbook. We are just asked to evaluate the exponential function e raised to 1.7 plus 4.2 I. Right, so how can we do that? We know that e raised to z is nothing but e raised to x cos y plus I sin y. So we'll just substitute the value of x and y there. That is, we will determine what is e raised to, here x is 1.7 and y is 4.2. So we'll determine what is e raised to 1.7 into cos 4.2. It is given to be minus 2.683, and e raised to 1.7 into sine 4.2 is equal to minus 4.777. So you can use your calculators to determine the corresponding values and find the exponential function in a very simple manner. And also there is a simple example for a polar form, that is, if we are given any polar form, any complex number z is equal to 1 plus I, then what will be the corresponding polar form? It will be what will be r of 1 plus I? R will be nothing but root of x square plus y square, that is root of 1 square plus 1 square is 2, so it is root 2. So r is root 2, and theta will be equal to tan inverse of y by x, and here it is pi by 4. So corresponding, we can, given any complex number, we can find the corresponding values of the magnitude, that is of r and of theta, which is the argument, and we can easily determine what is the polar form of that complex number. So that's it about exponential functions. Thank you all. Stay home and stay safe.